Now we're going to take and expand the between groups, like one-way ANOVA, to more ways. So what exactly does more ways mean, and how does that relate to a factorial ANOVA? That's what we're talking about here. So when we did a one-way ANOVA, we compared baby food, brands of baby food. We had Beech-Nut, Del Monte, Gerber. But the groups only differed on one dimension. It was just the different in brand. The actual type of food was held constant. It was always strained peas for all of the brands. So what Factorial does is it introduces sort of more ways in which to compare groups across different dimensions. So we're going to talk about what is meant by factorial. We're going to go through an example. It's going to be more baby food. We're going to talk about some assumptions and how to do the analysis, and then even go into talking about multiple comparisons following a factorial design. And then we'll go into effect size estimates. And then at the end, this is almost like a little bit of, if you remember those Scared Straight, where they would show kids' videos of what happens to criminals and things like that to keep them from a life of crime. Well, these higher order designs are meant to sort of scare you away from ever doing them. We're going to talk about them and talk about what it means when you have, you add more and more ways in which to compare data. So going from a one way to a two way to 3, 4, 5, 6 more ways. So this is the original example. We did this in the one way. I compared Beech-Nut to Del Monte to Gerber. We talked about how to do that as a one-way ANOVA. And that one way was simply comparing the brands and keeping everything else sort of constant. And we looked at, Gerber 1, at least, compared to Beech-Nut, there was a significant difference, and we were able to make some conclusions about that. At least, there were some significant differences between the brands, and it looks like it looks like Gerber at least won out compared to Beech-Nut, but anything else maybe a bit inconclusive. We don't know enough, there's not enough differences between them to know anything else. But then the question comes, all right, so Gerber won, or at least compared to Beech-Nut, there was a difference there, but did it? And the reason I ask that is because Gerber, if we're looking for the best brand of baby food, well, Gerber only won out when it comes to strained peas. Maybe Gerber isn't the best at other kinds of food. Maybe Gerber is only good at strained peas, but at other types of food, Del Monte might be the winner, or Beech-Nut might be the winner. So we're going to try to expand it out and see if this idea that Gerber beats out at least Beech-Nut is consistent with other types of food. So what does factorial mean? And what do we mean by sort of one-way versus two-way versus three-way? So factorial means that you have at least two IVs. So the minimum factorial design is going to have at least two IVs. And all levels of one variable occur in combination with all levels of the other variable. So every conceivable combination occurs. So if I have 3 levels of brand and 3 levels of type of food, which we'll talk about in a second, every brand has to exist in combination with every type of food in order for it to be fully factorial. I'm just going to mention quickly the assumptions. Really, they're the same. Nothing's changed. It's the same as they are for ANOVA. They're just tested in more places because we have more cells. We have more things to look at. But they're the same. We're assuming a normal distribution of our sampling distribution. We're assuming that the variances are homogeneous. And we're assuming that the scores, the actual responses, are independent, because this is a between groups. It's an independent samples type of test. This is, again, expanding our independent samples t-test even further. So in the simplest form, if we think, generically, okay, we can think about having some kind of IV we'll call A, right? So this is IVA, and IVA has 2 levels. It has A1 and A2, whatever those are, it doesn't matter. This is sort of just generic. There's an A1 and A2 levels, and with B, which is a second IV, a second independent variable, we're going to have 2 levels there too, B1 and B2. And the reason what makes this factorial, as you can see in this sort of box, is that each of these represents a combination. So here I have A1, B1. This is A2, A2B1. This is A2B1, and this is A2B2. Okay. So every combination exists. That's what makes this factorial. Okay, so every level of A exists in combination with every level of B. So to put into some perspective, we had talked about sort of the Grand Theft Auto versus Lego video game in our independent samples test. And we came to some conclusion that, Grand Theft Auto led to significantly more aggressive behaviors after gameplay. Okay. But we only looked at video game. We didn't look at any other variable that might be affecting aggressiveness, like gender or sex, or however you want to define it. Looking at, I'm using gender here to refer to men versus women as opposed to male, female. But so let's say we randomly selected groups of men and women and look at them separately and how playing Grand Theft Auto versus Lego impacts them. So, like, again, every combination exists. So here is Grand Theft Auto being played by men, right? So it's Grand Theft Auto men. Here is Lego men. Here is Grand Theft Auto women. And Lego women. That is what makes it factorial. Right? Everything exists in combination. So if we were to do this, what kinds of questions could we ask? What kind of questions can we ask with a design like this? Well, there's some obvious choices here. We could ask the same question we did before, which is, does playing Grand Theft Auto impact your aggressiveness differently than playing Lego does? And all things sort of apply. We use Lego because it's a similar nonviolent game to GTA, etc., etc. And we can actually ask that same question. We can ignore the genders for a second and say, look, is the mean of GTA different than the mean of Lego? Right? And all that would do is it allow us at least to make sure we're including men and women, right, in the same thing, because we're basically going to be ignoring the fact that they're men versus women and just looking at everyone who played GTA versus everyone who played Lego. That's one question, right? We could also look at, there's not enough space on this side, but we can also say, well, what about we could ignore video game for a second and just say, look, who's more aggressive, men? And compare that to the mean for women, right? I can actually look at a mean for men and mean for women, and I can make a comparison there. That could be a different hypothesis. I can compare men and women together. Basically ignore video game altogether and just say, look, regardless of what they played, who was more aggressive after they played it? Okay, we can do that. We could stick to just that. Do just the means of video game versus, and then look separately at the means of the gender. But in here is where things get sort of more interesting, right? We actually have these combinations of gender and video game. So why not look at the means of each of those? We can actually then look at the mean for men playing GTA, the mean for women, the mean for Lego, and the mean for Lego men, mean for Lego women, and actually compare those four means. Okay. So when I'm looking at an overall difference, like if I'm looking at one IV alone while ignoring the other IV, or sort of what they call collapsing the other IV, right? So if I'm comparing, say, the mean of all men versus the mean of all women, or I'm comparing the mean of Grand Theft Auto versus the mean of Lego. Right, if I'm doing those comparisons, these kinds of comparisons in a factorial ANOVA are called main effects. These are the main effects. They're testing each of the IVs separately. Right? You're getting an idea of the main effect of gender, the main effect of video game. Okay. Now, when we start to look at how these four cells, because what you might expect, right? If my hypothesis is a little bit more complex, right? What I might expect is that for men, playing Grand Theft Auto may lead to more aggression than for playing. For men playing Grand Theft Auto should lead to more aggression than playing the Lego game. But for women, maybe there's no difference. All right, so now I have a more complex idea that video games may impact the genders differently. Right, so if my hypothesis starts to become it starts to take shape as I think the effect of video game play on aggression depends on gender. I'll say it again: is the effect of video game play, does it depend on gender? If it does, then I am hypothesizing an interaction. So one of the things that these sort of factorial designs do is they allow us to test hypotheses as if they were like one-way ANOVAs by themselves. I can do just men versus women. I can do just Grand Theft Auto versus Lego as separate one-way ANOVAs, or even as independent samples t-tests. But what I can't do in either of those sort of alone is to see how do those variables impact one another, or work together to impact the outcome, which in this case, aggression. So it's often the interaction that is interesting in why we tend to want to do these kinds of designs, these sort of 2x2 factorials, or 3x2 or 3x3. We tend to want to see how do the levels of the IVs work together to impact the DV that we can't see by looking at the main effects of the IVs separately or independently. So it's this interaction that makes this interesting. So we have to get two main effects, an interaction, and all of it. We're going to be able to test all of that for a single alpha equals 0.05. Right? So we're going to be able to do all these things. We're going to get three separate tests, right? All with one alpha level controlling for the type 1 error. Seems like a pretty good deal. Right? I'm doing essentially one analysis that's giving me the answers to three different questions, all for the price of the same price of admission, right? That we had when we did an independent sample t-test or a one-way ANOVA, right? So this is very cool. It actually allows us to do lots of things with the same alpha level and the same assumption about type 1 error. So let's give a more detailed definition of what we mean by factorial and interaction and all those things. So performing a factorial analysis does the job of three analyses in one, as we just saw, right? We have two one-way ANOVAs, one for each IV sort of separately, that we call a main effect. And then we get an extra test, an extra comparison, an extra hypothesis test that is for the interaction between the IVs. So let's give a nice definition for interaction. The interaction is the effect. So anytime the effect of one IV depends on the level of another IV, that's an interaction. So in that particular example, if someone were to say, well, does playing violent video games lead to more aggressive behaviors? And you'd say, well, that depends on the gender of the person playing the video games. If that statement is necessary, that it depends on, then you likely have an interaction. There actually is some limit or some specific effect that it has on one gender versus the other, or one group versus the other, when it comes to looking at the effect of the second IV. All right, so it's the variability that is left over after you assess each IV. All right, so let's unpack that for a second. If we go through and we look at the effect that Grand Theft Auto versus Lego has, and we look at the effect that men versus women has on aggression, if that explains all the variability that exists in the data, then there is no interaction. There's nothing left. The main effects explain everything that we need to know, and there's no leftover variance that needs to be explained. However, that's often not the case. Usually we'll do a test for, for video game, a test for gender, and there's lots of variability that isn't error. It isn't within groups error. It's like between groups variability that we cannot quite explain with just the main effects. So it's an interaction is the variability that's left. There's additional variability between those four cells that isn't quite explained by the main effect for video game or the main effect for gender. Another way of thinking about it is the two IVs together work to affect scores over and above either of them independently. So let's unpack that. Because we test the main effects for each one sort of independently of the other, independent of the interaction, we are testing to see if, if the differences between the video games, differences between the genders, if it's significant or has an impact or whatever it is, we're looking at that. So what the interaction represents is that because there's leftover variation, there's some between groups variation that we're not able to explain with those two main effects, it must mean that the two IVs are somehow impacting one another in a way that is over and above, that is separate, that is independent, that is on top of, that is extra relative to the two main effects. Okay? It's a really goofy example, but I sometimes like to think of it this way, where if you were to have, you assign people to either have, I don't know, let's say either they're going to get like chocolate or no chocolate. Okay? And they're either going to get ice cream or no ice cream. Alright, so for the most part, relative to like, these people got nothing, right? They get nothing. So relative to getting nothing, getting chocolate is better than getting nothing. Alright, so this is chocolate sort of only. And also, compared to nothing, getting ice cream. So this is sort of ice cream only. Ice cream is better than nothing. So it's likely there's going to be main effects for comparing, chocolate to no chocolate, ice cream to no ice cream. But here, these people are getting both chocolate and ice cream. And it's likely the combination of chocolate and ice cream together, okay, maybe doing something differently. The fact they're getting both of those things, the combination, that they actually might respond in a way that is not explained very well by just the chocolate versus no chocolate, ice cream versus no ice cream. And this cell here represents sort of something they call it a synthesizing effect, that the two together are actually impacting people's scores on happiness or whatever it is they're measuring them. It actually impacts their scores in a way that is over and above, that is extra, on top of the effects for getting just ice cream or getting just chocolate. Again, this is a goofy, overly simplistic example, because maybe it's not the chocolate ice cream combination, the fact they're getting two things, or they're just sort of additive. But the fact that even if you add ice cream and chocolate together, when looking at just no chocolate versus chocolate, no ice cream versus ice cream, it's not going to capture necessarily that this is going to be a much different group. Even if you're just looking at the additions of the two together, there's still something over and above either of those things working independently that's going to lead to some kind of interaction. Okay, so the two IVs together work to affect scores over and above either of them working independently. That makes sense, right, with this example. All right, so still talking about sort of expanding the ANOVA. The between group sums of squares for a one-way ANOVA gets further broken down. So in a one-way ANOVA, it was there was just three things to worry about. We had, there was a sum of squares total, and that equal to a sum of squares between groups, and that, plus sum of squares within groups. And that was it. We had to find those three sums of squares. All right, so before, our sum of squares between groups was just one effect. It was just a single thing. There was only one way. That's why they actually call it a one-way ANOVA. There's only one way in which groups differ between each other, between themselves. Well, now we have multiple ways in which groups can differ. So if you think about the generic example, they are going to vary around IVA. They're going to vary around IVB. And then there's that extra bit of variation that we get from the A by B interaction. So now the sum of squares between groups, which used to just be a single thing, was one thing, is now getting broken down into three things. The sum of squares for main effect for A, the sum of squares for the main effect of B, and then the sum of squares around the interaction between A and B. So in a 2IV factorial design, A, B, and AB all are differentiating between groups. So therefore, they're all part of what we thought of before as just sum of squares between groups. They're all some component of the sum of squares between groups, and we need to sort of break them up and separate them out a little bit. Okay, so now this between groups is being split. So instead of just being total between and within, I now have total A, B, and the interaction plus our within groups. Okay, so now we're expanding out to more sums of squares. We're going to have sum of squares for each of those effects, the two main effects and the interaction. All right, so this is now our new data set, where I now have the brand is now IVA. Okay, so IVA is now the brand of baby food. It's the same: Beechnut, Del Monte, Gerber. Nothing's changed. But they've now expanded it out. So we have the original strain peas that we have from our first one-way ANOVA. They've also added in potatoes and carrots as three different kinds of baby food, three different types of baby food. And we want to be able to see if there's differences between the brands. And we do want to know if babies prefer different types of food, sure. But what I really want to know is is there a different pattern between the brands of food at each of the different types of food? So it looks like here, it's very possible that Del Monte is the preferred food when it comes to carrots, or the preferred brand when it comes to carrots. But Gerber is preferred when it comes to potatoes. And it looks like maybe Gerber and Del Monte are more or less tied, but are better than Beechnut when it comes to peas. And so we're getting different patterns. Those different patterns are really saying, when you ask, well, what brand is better? And you have to respond with, well, that depends on the type of food. And if that's there, if that dependency is there, then you're talking about the presence of an interaction between brand and type. So how does this help in our quest for the best brand of baby food? Well, a lot of people when they shop, a lot of parents, I imagine, at least that's the way my wife and I were when we had kids. If we're looking for baby food and we came, we'd say we liked Gerber, we would buy everything, everything from that same brand. But maybe that's not the way to go. Maybe, we should be buying potatoes from Gerber, but carrots from Del Monte. Right? And maybe it doesn't matter if we buy Gerber or Del Monte for strained peas. We buy either one of them. So this is a way of sort of looking at which of the brands is best within each type of food, which will give you a different answer. It's going to be a different answer. Now, the other way, it's not reflected in the data set, is this may help us to generalize. So the first time we found that Gerber was better than Beechnut. Okay, awesome. But that was just for strained peas. Now we could have done this and maybe found out that Gerber was better than Beechnut at potatoes and for carrots too, and that pattern is the same, meaning there's no interaction. The difference between the brands does not matter. It doesn't matter what type of food you're using, that you're feeding the babies. Gerber's preferred across the board. Everyone likes Gerber better. So that is a lack of interaction, right? So when people say what brand is most preferred, you say, oh, Gerber, because it didn't matter. Then that lack of interaction is also helpful because it tells us that the effect of the differences between the brands, well, it generalizes to all three of these types of food. That's not the case here, at least that doesn't look that way because of the numbers in here. But let's say it was all 999, 999, 999 all the way across the board, and it was better than everything. Then we could say that there was no interaction, and the effect that Gerber has is sort of the same across all types of food, or at least these three types. So it helps us to figure out if there is a dependency, or if effects that we found, like the one ways, help to generalize across multiple types of food. So it's very helpful. Again, if I'm the brand manager for one of these companies, or if I'm a market researcher and stuff, these might be the kinds of things I'm trying to figure out. What is it about the potatoes that make Gerber that much better, or that Del Monte does differently about their carrots that make So I may want to know what's going on and why you're getting different patterns depending on the type of food being used. So questions that can be addressed by this. So we talked, generically about the video games and gender, but what about for this baby food and brand versus type? So is there a difference in preference across the brands? So this is the same question. This is a main effect. It's the same question we asked previously in the one-way ANOVA. Do babies prefer one brand over another? Is there a difference in preference across types of food? So this is a different question that maybe we may not be that interested in overall, but it's there. It's part of the ANOVA. Do babies just like carrots more than peas and potatoes, or do they like potatoes more than peas and carrots, or whatever? So we can actually find a main effect for the type of food. And the last one represents the interactions. Remember, these two are our main effects. Again, main effects, sort of written out. And the last one down here, this one alone, is our interaction. Okay. So does brand preference depend on the type of food? For instance, do babies prefer different types of food made by the three different brands? If the answer here is yes, we're going to be able to do a test for that. That means there's a presence of an interaction between brand and type. The question comes down to, how do we do a hypothesis test when we have all this stuff going on at the same time? And because it's doing it all together, it does sort of combine everything together in one. So our null alternative hypotheses are not just a single hypothesis. Remember, in a one way, it was all groups are equal, and the alternative was, well, they're not equal, not all equal anyway. So here, because we have the two main effects and the two interactions, well, we need to test them. We need to have hypotheses about them all. So for the two main effects, right? So all brand means are equal, and for the type, all type means are equal. Right? So it's the same idea, just we have one for each main effect, and then we have a null hypothesis for the interaction that is, well, there isn't one. There's no interaction present between brand and type. And those are the null hypotheses. So the things we're trying to either retain or reject as part of our hypothesis testing steps. And our alternative is similar. So if these are all brands are equal, all right, well, not all brand means are equal. If the null is all type means are equal, then the alternative is not all type means are equal, right? All it takes is for one of them to be sort of different, and we would reject that null hypothesis. And if the null is that there is no interaction between brand and type, the alternative is, well, there is an interaction between type or brand and type. And those are basically how you state the null and alternative. It's really stating three nulls and three corresponding alternatives. For 3 and 4, not much has changed. Alpha is still 5%. We still want it to be at 0.05, and still an assumption. It's like the convention that we all seem to sort of follow. Because we have more than one IV, we've sort of moved beyond a one-way ANOVA. There are multiple groups. They're sort of between, they're independently, independent samples. So it's between groups. So this has got to be a factorial between groups ANOVA. All right. So there's more than one IV. The IVs are crossed, or they're factorial, and they're assigned to groups sort of randomly, like we would assume with the between groups analysis variance. So this has got to be a factorial between groups ANOVA. So let's talk about step 5. So step 5 is where we got to deal with degrees of freedom, and we got to deal with our decision rule. So the first part of that, let's look at the degrees of freedom. So the way that, if you remember in a one-way ANOVA, the degrees of freedom between groups in a one-way ANOVA was simply k minus 1, where k was the number of groups. Okay, well, we now have groups being differentiated in different ways, and they may have different numbers of levels. Here it happens to be 3 and 3. 3A and 3B, but they don't have to. You can have 2 A's and 3 B's, or 5 A's and 4 B's, or whatever. So we're going to stick to that same general idea, but we can't really use K's by itself anymore because we now have multiple different types of groups. So oftentimes you'll see this says number of groups that for A minus 1. So the easiest way that you might see this written out, instead of using K and whatever, and they just use where A refers to the actual IV, right? Well, little a refers to the number of levels on that IV. And if you have something like A1, that is an individual level, right? One level out of all of them, right? So capital A refers to, generically refers to the IV. A is just the number of levels you might have. So I can rewrite this as just being A minus 1. The levels of A minus 1. This for B is simply the B minus 1. Because if A represents the levels of A, B represents the levels of B. Okay. The interaction gets a little bit strange because, as we'll see, the interaction really is a sort of multiplicative or multiplying effect. It is, the effect of A times the effect of B. That's why it's usually called AB or A times B effect. So what you're seeing is here, the degrees of freedom for the interaction is really just the degrees of freedom for A times the degrees of freedom for B. So A minus 1 times B minus 1 is really, that's it. I mean, that's really the degrees of freedom for it. Okay. Now, in a one-way, so this is sort of our one-way sort of reminder corner, our degrees of freedom within groups equal to our total n, which is n1 plus n2 plus n3, so on and so forth, was n, total n, minus the number of groups, because you lose 1 degree of freedom per group, because we have to estimate a mean for each group. Okay, awesome. So there's our sort of one-way reminder, n minus k. So we got to think about how many subjects do we have here? Well, I still have n of them. So n still refers to all the subjects. Take all your participants, the total number you have, that's still n, that still works. But why are we subtracting A times B? Because A times B represents the number of individual cells or individual means that we're going to have to compute. Let's go back 1 second to our example here. You can't really see it very well, but you have our this is one cell, peas, beech nut. Another cell, potatoes, beech nut, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 different small groups that are made up of the combinations of type and brand. So we have 9. So how do I know I have 9? Well, I have 3 levels of A that have to be factorial with 3 levels of B. So think about this down here. I have A1, A2, A3. I have 3 levels of A. I have 3 levels of B. So how many individual cells am I going to have to deal with? Because each one of these is going to require us to compute a mean. There's going to be means for each one of these that we're going to have to use when computing the interaction and etc. Okay, so each one of these represents an intact group of participants. Right? They were randomly assigned to one of these 9 different groups according to our example. So how would I go about figuring out how many of those groups I have? Well, if I take the number of levels of A, which we just say is A, right, we have A levels, and I have for B, I have B levels. So it's simply just A times B. So 3 times 3 is 9 cells, which means I have 9 individual groups. So really, it now takes the place of my n minus k. Because k before was I'm losing 1 mean per group, and I have k groups. Well, same thing here. I have A times B number of groups. So I'm taking my n minus the 1 mean for each one of these groups. Means I lose a degree of freedom. So degrees of freedom now are going to be n minus AB. And total is just, again, n minus 1. Take your total number of subjects minus 1. And it also works out that it's the degrees of freedom for A plus degrees of freedom for B plus the degrees of freedom for the interaction plus the degrees of freedom for within groups. All those things are true. All right. So in our example, if we want to figure out degrees of freedom, we need to know, I know I have 3 levels of A, 3 levels of B. In each one of these, little n for each one of these equals 3. How do I know that? Go back, I think it's messy, but go back here for 1 second. So you can see that in the peas, beech nut peas group, there are 1, 2, 3 babies. In the Del Monte peas group, there's 1, 2, 3 babies. So my little n is 3. So how do I want, if I want to figure out what n is, big N, and if every little cell has the same number of participants, I can simply take A times B times n will equal my n. This only works if n is the same to every single group. So 3 times 3 is 9, times 3 means I have 27 total participants. And if you want, you can go back to this and count them. There are, in fact, 27. Okay, 27 babies were randomly selected and then randomly assigned to one of these 9 different combinations of brand and type. All right, with all that being said, we can now figure out degrees of freedom. So A is 3 levels, so that's 3 minus 1 equals 2. B also has 3 levels, so that's 3 minus 1 also equals 2. Well, 3 minus 1 is 2, and 3 minus 1 is 2, so I know that here this is going to be 2 times 2, which is going to be 2 times 2 equals 4 degrees of freedom for my interaction. I have 27 people minus my 9 cells. Right? That means I have 18 degrees of freedom there, 18 degrees of freedom for within groups. And for total, even though it has all this stuff here, it really comes down to just being our 27 total participants minus 1, which means there's 26. And because this says here that degrees of freedom for A plus B plus the interaction plus error should all add up to total, we can check. 2 plus 2 is 4. 4 plus 4 is 8. 8 plus 18 is going to be 26. And so all the degrees of freedom do add up to the total degrees of freedom. And I now know that my degrees of freedom, which I can put here, so degrees of freedom for A equals 2, degrees of freedom for B equals 2, degrees of freedom for A times B equals 4. And then if I want the degrees of freedom for within groups equals 18. All right, so I need to know those things in order to find out stuff on that very next page. So remember, the whole point of this is we're back at step 5, right? Step 5. I need to look up my degrees of freedom so that I can look up an F critical value for the test. Now that we have our degrees of freedom, we can start to look up our F criticals. The way F criticals work, as we saw in our one-way ANOVA, is that we need the degrees of freedom between groups, and we need degrees of freedom within groups. So it's still the same. So if I'm going to look up an F critical for my A effect, I need 2 and 18. For my B effect, it's 2 and 18. For the interaction, again, it's not going to be 2, it's going to be 4 and 18. So for both A and B, I want to have the same critical value because they're the same degrees of freedom. And then we have a separate critical value for the interaction that has 4 and 18 degrees of freedom. So here we can see the F critical for 2 and 18 is 3.55, and the F critical for 4 and 18 is 2.93. All right, well, let's see how we got those. All right, looking here, we have our F table for our conventional 0.05 alpha. And as we said before, I have 1 degree of freedom that's 2 and 18, so 2 degrees of freedom for between, and 18 degrees of freedom within. So I go 2 down to 18, and I get 3.555 or something like 3.56. For our interaction, I have 4 degrees of freedom here for the numerator, the between. And I scroll down to, again, 18, I get 2.928 or 2.93. Okay, so they only differ by these 2 columns, 3.555, 2.928, so 3.555, 2.928 is then our other value. So I'm looking, it's probably 3.56 and 2.93 if you're rounding to 2 decimals. So you might notice from a second ago, I looked it up on the table and I realized that I might as well just make them the same. So you now see 3.555 and 2.928 are the values from the table. Just copied them over, changed it so it would match. So that means we have an F critical at 3.555 that applies to both my A and B main effects. And then I have a 4 and 18 degree of freedom critical value at 2.928 that applies to my interaction. So our decision rules will sound something like this. If the F for brand, the F test for brand, is greater than, so instead of thinking about it as F observed, because they're all F observed, but instead of thinking about that, because we're going to have 3 different ones, I was trying to keep them separate. So the F observed for brand is greater than 3.555, we're going to reject that brand null hypothesis. If the F observed for type is greater than 3.555, I'm going to reject the type null hypothesis. And if the F observed for brand by type is greater than 2.928, I'm going to reject that interaction null hypothesis. So it's interesting here that unlike a one-way ANOVA where you're either going to retain or reject, it's possible to reject on some and retain on some. You actually may have a mixed bag where some hypotheses get rejected, some get retained. It depends on the outcome of the test. You may have 2 significant main effects, but your interaction is not significant. You may have significant interaction, but your main effects aren't significant. It's all, different combinations are possible. They have different degrees of freedom and different critical values. And of course, they may or may not have an effect. There may be nothing there. So in step 6 is when we get into the analysis, which we're going to stay on for quite a few slides to sort of go through and sort of talk our way sort of through it. So for sums of squares, we now have to sort of break things up in a different way. In reality, total is essentially defined in the same way. If I ignore all the groups and just look at one grand mean, all the scores around that grand mean or deviating from the grand mean, that's total. I'm still going to square, it's still going to do the same kind of stuff. It's going to be scores from the grand mean. Within is also essentially the same thing, because when we look at the individual groups, I want to look at how much the scores deviate from each of those cells. Now, the word cell is interesting, as I'm thinking about, instead of thinking about groups and having different terms, because you have, you know, A1, A2, A3 is different A groups, and you have B1, B2, B3. So anytime there's a combination, like an A1, B1 cell, like the beechnut peas cell, right? The term, I'm going to use the term cell to refer to that smaller component, where it's like an individual. It's like the smallest level at which the babies are, in this case, the babies or the participants are being randomly assigned to. So they got randomly assigned to 9 different conditions, and those are the cells of the design. So if we look at how much the scores deviate from the means of in each one of those cells, well, we're really getting at the within groups. How much are people deviating within their own group? Well, their own group is defined as the smallest level which they were, you know, randomly assigned to, which in this case again is all the combinations of brand and type. So we have 9 different cells, and I want to know how much are participants varying from the means of those cells to get it within groups sum of squares. For the between group stuff, again, it's been split. Remember, because A and B and AB, these were all sort of part of, or, you know, they were all sort of collected together before and sum of squares between groups. Right? They were all just different ways of looking at between groups. And the reason why they're all between groups, you're thinking, well, how does that work? If I was to pretend for a second that I had a one-way design in which I had, let's see, let's try these. So this is 1, 2, 3, 5, 6, 7, 8, in which I had 9 different cells, right? This is my, you know, Gerber, let's start from the bottom. This is my beechnut, peas, beechnut, I guess I got a PE, beechnut potatoes, beechnut carrots. This is now Del Monte peas, Del Monte potatoes, and Del Monte carrots. This is now Gerber peas, Gerber potatoes, and Gerber carrots. I could think about this design as just, well, look, I have 9 groups. I have 9 groups of babies, and I assign them a different brand baby food combination. And I can do this as just a single sort of, you know, one-way design. If I did that, the differences between those 9 cells would be this sum of squares between groups. It's just, I want to break it up and look at, well, I want beechnut versus Del Monte versus Gerber, which is my A effect. So I'm going to take the sum of squares between groups. I'm going to do part of it as, okay, well, how much do the brands differ? And then I also want to look at, you know, peas, these 3, versus potatoes versus carrots, which is my sum of squares B. And I'm also going to look at, yes, I want to look at the 9 cells, but I want to look at how much those 9 cells differ from each other in a way that isn't A and isn't B, and that's going to be part of this interaction. So all 3 of those together are going to end up being our between groups, all combined. So we're going to have to find one for each of those, and then also find our within groups, which in this sense you can call like sort of within cell, right? Because if this were a one-way, I'd be looking at the within groups within each one of these little boxes, little cells. So my within groups, really in a factorial, is my within cells variation, within groups variation. Okay. Before we look at all that stuff sort of laid out as an equation, so we start moving towards how to actually analyze and calculate those values. I just want to mention that what we do know so far, we know there's A, there's B, there's interaction. We know we need within groups. We know that A and B have, you know, different levels. You know, so all the stuff we need to keep in mind as we sort of look through the equation. And I want to make sure that when you look at the equations, where I sort of blank things out, so I can sort of warn you. Look at it, this equation looks very long and very complicated, but it really isn't. It's just taking the same things we already know about a one-way ANOVA, how to calculate sums of squares, and it's just expanding it. So there's a lot of information there. We're going to go through it part by part, but don't freak out when you see the equation on the next in the next bit here. Okay, so here it is. It says a lot of stuff. You're like, oh my god, so many sigmas. Why so many sigmas? Because we end up summing over lots of different things. Okay, so let's take it part by part. So remember, A represents the levels of A, B represents levels of B. To indicate that we're talking about individual levels, we now have subscripts. So the J is just the stand-in for the level of A. All right, so A1, A2, A3. Right, those are all represented by J. Just generically, we're going to have an AJ level. And just to separate them out, to make sure that we can have different levels at different times, I'm using K. I know that K was, groups for the one-way, but I'm using K here to represent the generically levels of the B IVs. These are now levels of type. So I could have an A1, B1, which would be my beechnut peas condition. I can have an A3, B3, which would be my Gerber carrots condition, right? So it's just a way of referring to the different places, different cell combinations that we might have. And then you have next to it, you have I, and I represents the individuals, so individual scores. So anytime you see an I in there, we're going to be looking at the individual scores of participants in those cells or wherever it is we're looking at. So usually, if you have an I there, it's going to be this sort of AJBK because we're looking at every individual and every combination of A and B. I want all 9 cells, and I want every individual score in all 9 of them. So when we're summing up, I want each individual person around the grand mean, and I'm doing 27 different deviations. I know I have 27 babies in this example. So I'm going to do 27 deviations and scoring them. Well, how do I get those 27, and how am I adding up 27 different things? Well, I'm taking my 3 levels of B, my 3 levels of A, and my 3 levels of I, my 3 individuals per cell, and I'm summing over all the individuals in all A and all B levels, which is why there are 3 sums. Okay, so I'm summing up all those things. So if you haven't guessed yet, this represents the sum of squares total. Okay, it's every individual around a single grand mean. So I'm now ignoring the fact it doesn't matter what brand they have, what type they have. Just looking at their scores with one average, and that's my grand mean. I'm looking at every single baby score in every group around that grand mean. That's it. This is my sum of squares total. So here, notice that there's no individual, there's no I, and B is not involved. So it means I'm only averaging over, so I'm ignoring B, and I'm averaging over I, because I is not there. So I want a mean for every A level. So I need a mean for A1, a mean for A2, a mean for A3. So that means I'm getting a mean for beechnut, a mean for Del Monte, and a mean for Gerber. And I'm subtracting from those means each time that same grand mean. And each time I'm squaring it. And I'm going to multiply it by the n that is in each of those groups. So if I'm having a mean for A1, I want the n for A1. So the mean for A2, I want the n for A2. Okay? Multiplying all the way through. So this is the sum of squares for A, or the A effect, in our case, example brand. Okay. This one is the same thing, just in reverse, in terms of looking at the other IV. I have the mean for each BK group. So again, I'm ignoring A. So in this case, it's like A doesn't exist. I'm sort of averaging over A. So I want the mean for each BK level. So a mean for B1, mean for B2, mean for B3, which means I need the mean for peas, the means for potatoes, and the mean for carrots. And each of those means, I'm going to subtract the grand mean, same grand mean, and I'm going to square each time, and I'm going to multiply by the n that went into that mean. So whatever the mean for B1 is, I'm going to take the n, the number of subjects or scores it took to get that mean, and I'm going to multiply it out here by the n for B1. So if I'm getting the mean for B2, I'm using the n for B2. The mean for B3, the n for B3. So this is my sum of squares for B. Okay, this part in the parentheses can be a little both intimidating and maybe a little confusing at the same time. A lot of people, when they look at this right away, just from from previous courses they've taken stuff, you want to start to cross things out. I can get rid of this, I can get rid of that because I can cross them out with this and start to solve for things. But that's not it. Okay, we're actually going to try to get at the interaction in a little bit of a backwards way. Not backwards, but we're going to use what we know about the sum of squares between groups to solve for it. Remember I said early on that the interaction basically is the variance left over after we account for A and for B, for the main effects of A and B. So because we know that the sum of squares between groups, right, all of it, all the sum of squares between groups equals the sum of squares for A plus the sum of squares for B plus the sum of squares for the interaction between A and B. Well, I can solve for the sum of squares for AB by simply subtracting. So if I take the sum of squares, so the sum of squares for AB then is equal to the complete, the intact sum of squares between groups, okay, minus the sum of squares for A minus the sum of squares for B. But just to be clear, this sum of squares between groups contains an A and a B in it. Okay? So I can't just cancel things out, as we'll see in a second, because I'm actually doubling up on them. So I have an A here, I have a B there, and then this part right here, just this component, just this thing, right? This is the sum of squares between groups. Right? The overall sum of squares between groups. And again, it's as if we ignored the fact we had two IVs. We look at just a 9-group one-way ANOVA, that would be our sum of squares. So in this sum of squares between groups exists an A and a B already. So if I don't subtract these two out, I'm going to have too much, this sum of squares is going to be too big. So my sum of squares between groups, if I subtract out the effect for A, the effect for B, which is what these are, because these look the same. This is again my sum of squares for A. All right, this is my sum of squares for B. If I find the entire sum of squares between groups, subtract out the sum of squares for A, subtract out the sum of squares for B, what I'm left with, what this part is in parentheses, this thing here, all right? What I'm left with is my sum of squares for the interaction. So that part in parentheses is really the interaction term. We're going to get it by looking at the sum of squares between groups, the whole thing, the whole enchilada. And I'm going to subtract out the sum of squares for A and B, and I'm going to be left with sum of squares AB. That's what's in that parentheses. So let's walk through that a little bit. This says I need a mean for every A, J, B, K combination. So notice there's no I here because we're averaging over something. So something has to be averaged over, so it's the individuals. So I'm getting one mean for every A, B combination. So I need a mean for A1, B1, a mean for A1, B2, a mean for A1, B3, a mean for A2, B1, A2, B3, A2, B2, A2, B3, A3, B1, A3, B2, A3, B3. And that'll give us sort of all 9 means that we have for each individual cell. And I'm going to take those 9 means, I'm going to subtract out the same grand mean, I'm going to square each time, And I'm going to multiply by the n that it took to get this mean. So if the mean for A1, B1 took 3 scores, and I'm averaging over 3 scores, I want to multiply by 3, right? Because I took the n for that A1, B1 cell was 3, so I'm going to multiply this whole thing by 3 when I'm going to compute the deviations, okay? So this is the sum of squares between groups. I'm subtracting out A and B because they both exist in here. And you can tell that if I do the sum of squares between groups, and all of it is explained by A and by B, when I subtract that out, my sum of squares AB is going to be 0, or something very close to 0. That means we have no interaction. Only when I look at the sum of squares between groups, subtract out A and B, and are left with something more than 0, can we actually sort of test to see if there's an interaction between the two IVs. Let's look at the last piece. What's the last piece missing here? So again, back to triple sums. It's crazy. And we're back to individuals again. I need an individual in every single cell. It's the same thing as up here. I want every individual score. So there's going to be 27 of these, just like there were 27 up here. These are the same things. Up here, I subtracted out the grand mean. So I'm subtracting out the same score every single time. Down here, however, I'm subtracting out the mean of each group. It's the same thing as this mean. I need the mean of A1, B1, right? So the mean of A1, B1. I need every cell mean. I'm taking every individual score, every person, in this case baby, every participant score, and every group, every cell, minus the mean of that cell. I'm going to square it and I'm going to add them all up. And this is going to be, because of looking at the variation within each cell, this is my sum of squares within groups. All right, so I have all the pieces. Total equals A, sum of squares for A, plus sum of squares for B, plus sum of squares AB, which is the whole thing in those parentheses, plus sum of squares within groups. And once we have all those sums of squares, we can then figure out the F's for each one. Use the degrees of freedom, find mean squares, and go through that whole process. But I want to sort of lay this out so you can start to see and understand what these equations look like and what each piece means and why there's so many sums, so many sigmas up here. So let's just remind ourselves again sort of how these things are breaking down and what I mean by breaking down. Well, you have a sum of squares total, okay? So the sum of squares total. Sum of squares total gets, originally when we did a one-way ANOVA, it got broken up into 2 pieces, right? There was the sum of squares between groups, and there was the sum of squares within groups. And that was it. It was just those 2 sum of squares. So the total was really just between plus within. So all we're doing now is taking this and breaking it up even further. The sum of squares between groups is now sum of squares for A, sum of squares for B, and sum of squares for A, B. Right, so we're just taking that where this is at the level of a one-way ANOVA, right? And that's what we're doing it one way. Down here is what's going on when we get to a sort of factorial. Okay. Just further breaking down the sum of squares. Degrees of freedom work the same way. So my degrees of freedom total, okay, which equals n minus 1. Well, when we first did this as a one-way, that got broken up into simply, for between groups, it was just k minus 1. And over here, it was n minus k for within groups. All right. Well, again, because we have k is now broken up into different pieces. We have we can think of the number of groups for A and for B and all that stuff. These are now getting further cut up into different pieces. So where this is the degrees of, so the degrees of freedom correspond with A, of course, is A minus 1. These is B minus 1. And over here, it's just being broken up into A minus 1 times B minus 1. But they all add up to the same. When if we were to look at this as a 9-group one-way ANOVA, right, we'd have 8 degrees of freedom. Right, so if we looked at K minus 1, that would be 9 cells minus 1 equals 8 degrees of freedom. So that means these things should all add up to 8. Well, A minus 1, this is 3 minus 1 is 2. 3 minus 1 is 2. 2 times 2 is 4 for this one. So 2 plus 2 plus 2 plus 4 equals that same 8. Right? So the degrees of freedom we had, if we treat it as a one-way, are just being split up the same way that the between group sums of squares are being split up. Since we have multiple sums of squares, we're now going to also have multiple mean squares. And generically, a mean square is just a sum of square divided by degree of freedom. So we're going to do this same thing. Right? So we're going to calculate mean squares for A, a mean square for B, mean square for the interaction, and a mean square for within groups. Right? So we're going to use those to then calculate 3 different F's. We're going to have an F for A by taking MSA divided by MSWG. We're going to have an F for B by taking MSB divided by MSWG. And then we're going to have an F for the interaction by taking the MSAB divided by MSWG. Okay? So this expands when you have more IVs, and we'll talk about that a little later. But for now, because we only have A and B IVs, we just have A, B, the interaction between A, B, and then error, and we can use those to calculate our F's. So 1 for each main effect, then 1 for the interaction, and then of course the within groups, so we can divide them and get our F's. So each effect and interaction is a separate F test. We're going to calculate them in the same way like I just said. Whichever effect, now this is here generically as effect, meaning the effect for A, effect for B, effect for AB. And take that effect over MSWG. Since MSWG is our sort of error variance, it's our within groups, it's the variance that we cannot explain. Remember we talked about in a one-way that, you know, we're giving these babies different brands. I can explain why they might differ in liking across the brands, but I can't explain why babies that got the same thing didn't eat the same amount. That's a sort of random variability I can't explain. That's the same idea here. You have 3 babies that got, you know, like Gerber peas, for instance. I can tell you, or maybe I can explain why they scored better or scored differently than people who got, you know, Gerber carrots or beech nut peas or something. But the babies that are in the same cell, everyone that got Gerber peas, the differences between their scores I can't explain because they all got the same treatment. So that just sort of gets dumped into this idea of a within groups sort of random variation, a random error that we use as our denominator in a lot of our F tests. Okay, so this is going to be calculated the same way, and as we saw in the steps, you look up a separate F critical for each test using the degrees of freedom for the effect and within, and you look them up using tabled values, which is what we already did in step 5.